Here's our final video on the VSEPR models. In the last videos, we've looked at linear molecules that usually have two atoms around the center, or it could just be a real small atom that only has two atoms. Then we looked at the trigonal planar and bent, structures that had three total electron groups around the center. Sometimes all three were bonding electron groups, and that was the true trigonal planar molecule. Sometimes there were two bonding groups and one lone pair, and the lone pair made the molecule bent. Similar things will happen with four bonding regions around the center. If all four electron regions are truly bonding electron groups, we call the structure a tetrahedron. Carbon loves to do these tetrahedral structures. Maybe for the sake of not having to draw so many electron dots, why don't we change this? Let's do CH4. Carbon tetrachloride would be exactly the same, but this one is a little easier to draw. Carbon has four electrons, valence electrons, and perfect. We hook on the four hydrogen. 2, 3, and 4. There we go. Okay, so again, when we're doing this electron geometry, or they might call it, what's the VSEPR shape, you usually want to draw the Lewis structure first. Then you're obsessed with the central atom. What's happening to the central atom? Specifically, how many bonding groups of electrons? How many non-bonding groups of electrons? In a tetrahedron, all four electron groups are bonding. So here's 1, 2, 3, 4. Those bonding electron groups are all negative. They'll repel and orient themselves as far apart as possible. Now here's the trick with a tetrahedron. The way that I have this drawn on paper, if I draw like a little ball and stick model, it makes it look as if these angles are about 90 degrees. It looks like 1, 2, 3, 4. It looks like this is a 90-degree angle. And it is not. We have to picture that these Lewis structures are just a two-dimensional drawing on paper. But in real life, this is a three-dimensional molecule. We want to get those four electron groups as far apart as possible. We can do better than 90 degrees. In real life, here is your three-dimensional tetrahedron. It kind of looks like a little rocket ship. In class, we'll build them, and we'll look at some digital simulations where you can twist it and turn it. It is a three-dimensional structure where this angle is actually 109.5 degrees. Can you kind of tell that it's greater than 90? That's what I'm most concerned with. I don't care that you remember 109.5. I want you to know that the angle is more than 90 degrees. That's important. So if I were to have a protractor or something, you can kind of tell that this angle here, that's more than 90. We can do better in 3 dimensions. So you have this little spaceship looking thing. It's one of my favorite shapes, the tetrahedron. From there, let's do this nitrogen, NH3. Nitrogen usually has a lone pair and 3 singles for a total of 5 valence electrons. Perfect. We have 3 hydrogen. 1, 2, 3. Link them up. Nitrogen has an octet. There are 6 bonding electrons and 2 non-bonding, for a total of 8. Or here we would say there are 3 bonding electron groups or electron regions, and there's 1 non-bonding electron group, that lone pair on top. That's this guy right here. This is the lone pair. put that in. These two, actually. These are lone electron pairs on the central atom. We're most concerned with the central atom when it comes to the shape or geometry of the molecule. Okay, so there's a total of 4 electron groups around the center, which makes me think tetrahedron. And so you really have to picture this tetrahedron, 3-dimensional little rocket ship in your mind. 4 electron groups as far apart as possible. However, one of the positions is not really an atom. So if I were to take my original tetrahedral structure, and if I were to pop off one of these atoms, look at what you're left with. I'm going to picture the electron pairs up on top. We call this a trigonal pyramid. Can you tell that that's 3-dimensional still? It's like a tetrahedron, but you remove one atom. So what you're left with is still 3 atoms, but they're kind of angular. It's not flat. It really is like a little triangle pyramid. It's different than this guy, the flat trigonal planar, where this really would be 2-dimensional. It's flat. Planar means flat, where the angles are a perfect 120. Can you tell how that one is a little different from this? Can you see that this is a little bit more of a pyramid? This is 3-dimensional. It's raised. Because of that lone pair, it changes the shape and it changes the properties. And that's what we'll look at in the lab. This trigonal pyramid has different properties than a trigonal planar. Now the formulas might look similar. Here's NH3. You could have BH3. Those formulas look exactly the same, but not until you draw it do you realize that their structures are different. Here's BH3. There are no extra lone pairs on the center, which makes these bond angles 120. However, in the trigonal pyramid, there we go, 120. These angles are about the same as a tetrahedron. We can call these approximately 109.5. In reality, they're a little bit less than 109.5 because the lone pair actually takes up a little bit more space than a bonding pair. And so the lone pair region kind of smushes the other atoms. But the angles really are approximately 109.5. I think they're a little bit closer to 108, 109. We'll just say approximate. And again, I don't care that you remember that number. I just want you to know, number one, the tetrahedron is not 90. No. Sad face forever for life with lots of tears. Tears, tears, tears. The tetrahedron is not a flat cross. It's a 3-dimensional structure. The trigonal pyramid is based on a tetrahedron, but one of the spots just isn't a real atom. It's a lone pair. Now look at this bent structure. Let's draw a water molecule. Very, very common. 1, 2, 3, 4, 5, 6 valence electrons. We'll hook the hydrogens on next to the single electrons of oxygen. Lewis structure, easy, right? Okay, so we're looking at the central atom. We have 2 bonding groups of electrons and 2 lone pairs, or 2 non-bonding groups. It's a total of 4. Can you see how all of these add up to 4? Here's 3 atoms, 1 electron pair, 2 atoms, 2 electron pairs. They all add up to 4. All of these shapes are based on the original tetrahedron. But now if you picture your original tetrahedron, your 3-dimensional little rocket ship, now 2 spots are not really atoms. So what if I pop off this one? Instead, now it's a lone pair. Can you see what's left? It's bent. It's not linear. If we have two atoms and either one lone pair, kind of like this situation, two atoms, but there's an electron pair that changes it, bent, as opposed to linear. Linear molecules have two electron groups, and that's it. No extra lone pairs on the center. In all of these examples, I mean, these don't have a central atom, I guess, but all of these guys have bonding electrons around the center, no lone pairs. That's linear. The extra electron pair, whether you have one electron pair or, in this case, two electron pairs, that changes the shape and it makes it bent. Now this bent is a little bit more extreme bent. You have to kind of picture that there's two lone pairs on that central atom. But again, these angles are approximately 109.5. Slightly less than. In reality, this is about 104, 105, because those lone pairs really do take up more space. So they do kind of smush the other two atoms a little bit. But again, these angles are all based on a tetrahedron. That's what I want you to understand, that they're all very similar. So two lone pairs is a little bit more bent than one lone pair, but it's the same general structure. It's going to look very similar. So again, all of these are based on 4 electron regions around the center. Now, one thing to caution you on with water, people will draw this as a Lewis structure. And I've always said you can organize your electron pairs and dots however you want. Then we hook on the single hydrogens, link them up, there you go. People that draw this for a Lewis structure, A+. There's nothing wrong with that Lewis structure. Lewis structures do not need to be drawn with proper bond angles. Here's the problem. Don't say that it's linear. It's not linear. And I have people that will argue and they'll be like, but I drew it in a line. I drew it looking linear. I get it, you drew it kind of looking linear. But in real life, these angles are not 90 degrees. Like from this electron group to this electron group, that's not a 90-degree angle. On paper, we draw it kind of looking like 90 just for the sake of drawing it. You don't have to draw it in perspective. But that's not a 90-degree angle in real life. So you're not working with something that looks like a T shape or a cross. In reality, you're working with something that looks more like this. I'll take off my gobbledygook here. There, let's get rid of all this junk. You're really looking at this three-dimensional tetrahedron where the angles are more than 90, close to 110. We want to get those 4 electron pairs as far apart as possible. In real life, if you remove any 2, it could be these 2, it could be these 2, whatever 2 atoms you remove and substitute with a lone pair, there's no way you can make this linear. It'll always be bent. So that might be my only caution, especially with water. You can draw your Lewis structure like this, and it's okay. A+ on the Lewis structure, you show the octet, you show that there are 2 unpaired, or I should say unbonded pairs of electrons, 2 bonding pairs for an octet on your oxygen. That's fine. But if they ask you for the shape, we have to be aware that there are 4 regions around the center, only 2 are bonding. If I visualize that tetrahedron and I remove any 2 spots and substitute lone pairs, there's no way I can make it linear. It has to be bent.